Okay, so this is something completely different, really. This is a paper. This is a paper which Mike Cruz is professor at Birmingham University, but he retired. We both retired a couple of years ago. Wonder what to do with ourselves. So it says. So really, the main motivation for what we did was about looking at low frequency gravitational waves. And this is really what the focus is. But in fact, what it is that one way of looking at low frequency gravitational waves is actually to see if they can be converted into electromagnetic waves, which I'll discuss in a moment. But of course, the problem with that is they will also be low frequency because it's a one-to-one conversion. So now the other thing is that it's also been proposed that earthquakes would also emit very low frequency electromagnetic waves, and therefore part of our thinking was that if we could obtain a way of doing this, then in fact it would also maybe help in that regard as well as a sort of early warning system. Right, so and also radio waves don't really easily penetrate water beyond a few meters, which is the reason why submarines, if they wish to communicate, they have to come to a surface, or at least they have to send up an aerial up, so obviously which makes them, it's dangerous for them if they're because they can be seen. So, but it turns out if they're very low frequency, then they'll go deeper. The radio waves will go deeper. So there are sort of other motivations, but the main one is about looking at gravitational waves of low frequencies. Now, just to fix numbers, just so that we all remind ourselves, the wavelength that we're talking about here is 10 to the 9 meters. We're talking about a hertz or 0.1 of a hertz or something. And just to remind you, the number's gone off the side there, but the Earth is smaller than that. So therefore, if you want to build an aerial, and usually if you have a dipole aerial, it's a similar size to the wavelength that you want to get, then of course this makes this totally out of the question. So therefore we have to find another way of doing it, and that's really what we set about doing, was to see if see whether it could be we could do it or not. So just to remind you, this is the source of gravitational waves. This is not a picture produced by me. But if you look at the bottom line here, this is the frequency of the gravitational wave. Then a lot of the interesting stuff, and I hope I won't be shot down by the astronomers in the place, but these things, there's a lot of stuff that's at a very low frequency. Now, LIGO and Virgo operate at the top, further up here. All right. So we don't have anything at the moment that will operate in this region. So, all right, so we're looking at less than 1 hertz or less than a hertz. And so one example is this thing called HM Cancri, which was news to me, but Mike pointed out, was that this is a pair of white dwarfs. Apparently they orbit each other and lose energy, and by doing that they're emitting gravitational waves. But if you look at the wavelength of the gravitational wave, it's right down here. So this is 10 to the minus 2. Well, a bit bigger than that, but it's very low frequency, and so so if we want to observe the gravitational waves, that is, then we need a way of doing that. Now, ESA set about this task, and this was done some years ago. There was a study done looking at all the various ways, and the one that they looked at, the one that they settled on eventually, was this one, number 3 on the list, which is a laser interferometry in space. We know it's Lisa. You know, there's been Pathfinder Lisa, which went up and actually was proved. It was like a proof of principle satellite, which proved that it could be done. And as you can see, that's going to operate in this 0.1 to 100 millihertz range, which is exactly the one that they want. So that was the one that they went on. But you can see there was loads of them. And one of the ones that, and the one that we were looking at was here, conversion of gravitational waves to electromagnetic waves, but in a static magnetic field, right? And this was first thought about, this idea was this guy here, Gershenstein, but it's not been done as far as I'm aware. Now, exactly how would we go about it? Well, if you look at this diagram, this silly diagram here,
Rob,
what?
could I interrupt? Just ask a very quick question.
Yes.
On the last slide,
Yes.
so these ones that are not selected because of TRL0, do you know what that means?
I do actually, yeah.
What was it?
I forgot. That's to do with the readiness of the technology.
Oh, okay.
So 0 to 9, as I recall, is the scale. 9 means we're good. We've got all the technology. We're good to go.
Okay.
0 means, you know, it's kind of like on paper.
Gotcha.
All right. And as you can see, the one that we chose, of course, was like TRL0, TRL0. And yeah, I was asked that question a little while ago and I didn't know the answer. So I had to go and find out. So I'm glad you asked. I didn't pay you any money, did I?
You didn't.
No, I didn't.
But you paid me extra to say that, right?
No, no. Right. Okay, so this is the Earth. All right, and this is the blue line is meant to represent the gravitational wave coming across, and it will vibrate the Earth. And of course, as we know, the Earth is also a huge magnet and produces a magnetic field. And the idea being is that gravitation, that vibration, I find it always very disconcerting to think that we're actually being bathed in these gravitational waves all the time. Luckily, they're not very strong. And that would vibrate this, and so therefore you would get an electromagnetic wave from that. And that's standard sort of Maxwell, as it were. You know, you vibrate a magnet, you'll get a radio wave. But of course, it's going to be 1 hertz or less. How do you do it? How do we pick that up? And that's really the thing. Now the trouble is that these are done in unitless equations, so that you can see it's the magnitudes which really hurt. So you got the flux of the electromagnetic wave, all right, and you've got this is the cross section of the exchange of the energy from one to the other. Then you've got the mass, and then you've got the frequency itself. And so, but as you can see, the cross section is very small for this stupid number. Now, but there are some other factors which work in our favour. Now, first of all, the Earth, the mass of the Earth is obviously large, and if you double that, obviously 44, square it, so you start to eat into this number, and gradually you think, oh, maybe it might be feasible to do this. So,
can I ask something? Why is it just for low frequency gravitational waves?
what is low frequency?
Why does it work for low frequency? I mean, the title of your talk was looking for the low frequency ones.
Yes.
Because I mean, the principle of having a gravitational wave vibrate the Earth and then produce an electromagnetic, that should be for any frequency, or
No, I don't know. Well, sure, there's a good reason. But I can't tell you off the top of my head. I think it's probably going to be, yeah, I have to think about that. But I think the thing is that once we put this together with the frequency of the gravitational wave, frequency of electromagnetic, like when you put these numbers together, I've got a feeling that it's going to work out such that that is the case. But I suppose really we did it the other way around. We were looking at how might we get a detector to look at these gravitational waves, of this in this band.
Oh.
So I think we were kind of seeing it from the other way around, if you see what I mean. But I think in principle, you're right. You know, you should be able to get anything coming out of it. So yeah,
Then you would get the electromagnetic waves in higher frequencies. that
yeah,
are
you would do,
easier
yeah, yeah.
to detect.
Well, not necessarily, because of course, as soon as you go to higher frequencies, you've got lots of background noise. Because you've got radio one or something, you know, you've got radio, TV, and all the rest of it coming in.
You don't want to compete with
Because you don't want to compete with it. See, the thing is, one moment, Peter, I'll be honest. The thing is about these very low frequency waves, we assume that there's nothing else, not naturally occurring, which will give you a massive step. You might get lots of spurious stuff.
Because talking about some models for dark matter and stuff like this, some of them, as far as I'm not an expert on that at all, but they predict having like high frequency monochromatic waves.
What, electromagnetic waves?
No, gravitational waves.
Oh, sorry,
There
high
are
frequency.
there are some models for dark matter.
So why didn't LIGO pick that up?
No, because they're very high for LIGO.
Well, what do you mean by high?
Like, I don't know, 10 to the 5, 10 to the 6, higher hertz.
Yeah. Well, if you were looking at radio waves or radio waves, I mean, I can't think off the top of my head, but you're really crashing into communications, aren't you? And I think then it would be a nightmare. I think, really. But, you know, it's a good point, good thoughts. But yeah, we chose this simply because we thought that it would be easier to distinguish. If you found something, it would be distinguished. Either you'd be off
Yeah,
there.
so the omega squared will that if you go to higher frequencies,
Well, it's low. Well,
won't that change your result at the end, your that number? I assume that
well, yeah, but we're doing. Sorry.
I assume that the 35, 10 to the 35 is significantly created by the omega squared from your relationship.
What have I done here? I forgot my own work. Shouldn't have drunk too much red wine last night. That's the mass, and then we got this is the magnitude of the magnetic of the wave of the gravitational wave. So this is okay, I got it now. This is actually picking out FGW, right? And FGW, obviously you've got the frequency of it itself, but also you've got the amplitude of the gravitational wave. And I think I've forgotten what this constant's for. What's that? Yeah, it's what distinguishes FGW. I'm sorry, well, mine's gone a blank, you know. But it's actually trying to give you a number to go in there. The idea is we're trying to put numbers in each of these slots. All right. And I've forgotten what the center of 35 is. I do apologise. Right. So the areas of uncertainty for this process will be converting the GR wave to electromagnetic wave is unlikely to be 100%. All right, so that seems reasonable. But the thing is, though, is that trying to produce any kind of model of the Earth's dynamo producing the magnetic field, and also all the layers of rock and so on. I mean, we don't have any knowledge of this, so you know we have to just hope that it's a reasonable number and gives us a reasonable signal. The level of background noise in these frequencies, okay, to our knowledge, there are no other sources. And I think this is really the thing that we kept going on about, kept coming back to, saying, well, there's nothing else there. So if we did find something, then it would be interesting. Because it would be very interesting if we did find something, but we didn't. But anyway, the level of noise, and also the last one, the level of noise generated by the electronics, well, that's something which we can measure. And this is a part of what we did, what we were trying to do was actually think about all these various parts to this process and the things that we could measure in good time, short order, and actually see if exactly where we're up to. So Now, what sort of antenna would we have? Now, for normal communication, the ratio of the wavelength to the length of the antenna, lambda over L, is normally between these two numbers. That's just standard antenna design. It's not normally larger than 10. The efficiency drops off pretty rapidly. So an antenna also has an effective area, and it's a simple relationship with the power. And it's just this power flux multiplied by the effective area is the power you actually receive. It's this thing, the effective area, because the first one is really out of question for us. It's this second thought that actually was the thing that we wanted to try and exploit if we could. So, and for a standard antenna, it's got this form. These are the resistances. The radiation resistance is the resistance of the antenna due to it transmitting radio waves. There is our losses, obviously ohmic losses in the conductors, all right? And also, of course, you've got a residual complex impedance, but it is possible to be able to tune these out. It is, in principle, possible to do that. So we want to maximise the effective area. Sorry, G is the gain, by the way. Sorry, I didn't say that. But you know, quite again, it's a number here where you think, well, it's only a gain of sort of 1.5, but at least you might be able to hear something. So, which antenna should we use? We looked at a dipole. Now, the trouble with a dipole is that again, you have to have this relationship between the lambda and L. And the radiation resistance is given by this equation, and the reactance has this form. Now, the problem with this is that the reactance gives you values of 10 to the 12, and that using passive components to try and tune that out is impossible. Well, impossible, it's not easily done. So, if you went to a simple loop, a simple square loop, with a gap across, normally you just have a square or circular loop. You measure it like a square, and then you have the two ends, and then you try and see if there's a voltage generated across the two ends. And this is so simple dipole was rejected because of this resistance too large to be tuned out. But this isn't the case for the loop. If you look at the loop, then in fact the reactance is a lot smaller, and then we can then have a go at tuning it out. And there's also we know this R rad from this equation. These are standard equations you can get out of the textbook. Right, now, so if you now look at the effective area at low frequencies, and just put in a 100-meter antenna, right? Okay, so you can see straight away with the frequency, you see this flow frequency, you can see the loop and the dipole, their effective area drops right off, obviously. It's quite low here. But notice in this region, somewhere around about the region we're looking at, you can see actually though the effective area for actually can this idea we might be able to exploit. So it's quite high, whereas these. And then eventually, of course, they all level off as you get further down into higher frequencies. So we thought, right, so we wanted to use a loop, and we wanted to try and reconfigure it in what we call a resistive antenna, right? And this is the reason why we chose this. Right, now resistive antenna is what I'm going to explain to you. And it's basically a loop antenna, but we've reconfigured it to. And what actually came, the inspiration for it came really indirectly, was at Birmingham. They actually do a lot of work on antenna, what have you. And there's this thing called a Salisbury screen. Now it's usually used to screen out microwaves, and it's excuse me. So the electric field obviously will induce a voltage in a conductor. Well, we all know that. That's exactly what the business we're in. Now the magnitude of the current would depend on the internal impedance of the source. Now, if it's coming from, if it's a radio wave, a microwave, for example, coming in, then the source is free space, and so therefore we know the value of that is 377 ohms, right? And that okay, we know that. So now we say that if the wavelength is shorter than the conductor, which is what microwaves, this is what these are used for microwaves. If they're much shorter, then in fact you don't get you do get voltages, but they become very localized. This is one of the things about this Salisbury spring. They become very localized, and they kind of whiz around, as it were. They actually get very localized, and they heat up the spring, and then all that energy is evaporate. Sorry, yeah, all that energy comes off as heat. Right, so let's say for the wavelength is shorter, but if it's actually much bigger, then in fact what you'd have to do is you have to then earth this, right? And then it would still work at some level. But the point is that so it's a bit so what we wanted to do, and these sheets are not conductors, they're actually they're actually resistance, they're actually a foam type substance. They're normally got nickel coated on them to give it conduction. So it's called a resistive sheet, and it's placed in this sort of sandwich configuration like this. And and it absorbs the microwaves. But as I say, if you then use it in a situation where the wavelength is much bigger than the sheet, then in fact you can still use it a bit, but you then have to stick an earth on it. So it was a bit obscure as to how we sort of come up with this idea. So then we thought, right, okay, let's take. Oh, I've got red light. Is that mine? My battery's run out. Oh, I'll use my finger. Right, if you take the normal loop, all right. So, but instead of taking just a continuous loop of conductor, you actually replace it with two conductors, R1 and R2. So the sides of them, and these have got different values of resistance. And then it turns out that if you earth it at the bottom as well, this is what you would do with this sheet. If that was a sheet, you'd earth it, right? And you have to have a very good earth, by the way. That's one of the things we learned, and it's been known for a long time, is that you got to have a very good earth connection. I don't know if any of you know this, but in fact, if I earthed it here, it wouldn't necessarily be the same as the one over there. And in fact, that causes safety problems. Okay. One of the, I mean, for example, if you've ever noticed aircraft being, I don't know what you call it, if you notice aircraft being fueled up, the actual fuel house has always got big earth connection to it. And that's because, you want to make sure that any residual stuff is, but it has to be very big. And normally around aircraft transit, you've got these huge things. And also on the experiment which I was working on in France just recently, the NEMO, before I retired, the NEMO experiment, when we took out the old experiment, you see this big copper grid on the floor, where in fact the whole detector was completely earthed through to the ground. And so earthing is actually quite important. So anyway, so the other, just come back to life again. Oh, okay. So the other end of the loop is connected to, now what you want to do is get the difference in the voltages across these two sides. And so you have a differential amplifier, all right, running into, all right, and then a spectrum analyzer, because obviously you pick up different frequencies and you want to see what they are. And it turns out that the effective area, all right, is now a function of this thing called F. This is L squared, so you've got the normal lengths involved, and F is made up of this. So you've got this equation here, which is for R1 for one side, and then you've got the other one R2, and then you see the minus the other ones. And so what you then do is you look at the various parts of this, But and then, as I say, the differential amplifier, because obviously this will produce voltages or a difference in voltages, and then that is what you use your differential amplifier to pick up. Right, so it's important that the current flows through the conductors, so it's natural to use the earth as a current sink. It can act as an efficient current sink so long as the voltage of the ground connection, right, does not change, right, as the current is delivered. Normally with the earth that is the case, but you have to stick a big in the ground to make sure. This means a high electrostatic capacity. So the capacitance of the earth is actually, again, it's calculated to 700 microfarads. So the sink resistance is given by this, and you can see as the frequency reduces, then this last term will dominate. And then the combination of the above gives you a better sensitivity at lower frequencies. So this is the point, is that when you put this all together, all right, you end up with a better sensitivity than the others. Low frequencies, I've got to keep stressing that. Now, the thing we had to do, first of all, was make sure we could actually pick up radio signals. And there is a place called Droitwich, which is out of town, up northwest of above Oxford, up that way. You keep going northwest and come to Droitwich, and they have they push out fairly low frequency waves. I'm talking about radio waves, normal sort of radio 4 stuff and what have you. And so we wanted to see if we could pick that up, which was a natural thing to do. Otherwise, we're not picking up some really dominating piece of radio waves. Then you can see it's not going to get very far. So that was our initial test. Let's make sure it actually works, right? And then we started looking at, we carried out noise tests. This is on the electronics and so on and so forth. And as you can see, the noise test, this is the noise test here. Okay, stupidly, I haven't got so you've got the ambient noise system, the system noise, we measured these things. This is at the different, this is at these low frequencies again. But the problem is that the signal that you're going to get from the things we want to look at, which is the super massive black hole mergers and so on, you can see the strength of electric field you're going to get is in here, and of course our noise is stopping us getting below this. So at the moment, the answer is, does this technique work? The answer is it's not good enough. It does work. And actually, for this problem, is better than the one we for other ways. But it won't. At this moment in time, we would have to improve this to get it right down here, so that we could then start picking this up. My own view. This one I'll finish. So the field trials and simulations are found to be consistent with the theory. We ran the theory through various simulation softwares, and it all seems to work out. From the measurements, a detection scheme on scattering gravitational waves, so through the Earth would seem to be, it would work, but we need to really get down. We need to get the noise down. So LISA, without doubt, is superior, and it will be once it's launched. The only trouble is, of course, is that it's getting it up there and getting it working. So we've not explored yet this earthquake detection idea or anything else. What we need to do, I think, and I stress this to Mike, is that we need to build a transmitter and then transmit and receive at these very low frequencies to see if, firstly, that we really are picking up very low signals, and it's possible to do this. But to transmit anything in this country, you need government approval, and so we've sent an application in, but we're waiting to hear from the Ofcom, the dreaded Ofcom, to see if they would. But the thing that I would feel happy about is actually exploring this about the earthquake detection. Saving people's lives always makes me feel a bit better than worrying about gravitational waves, which are very interesting, but they won't save everybody's life. So
Thank you.
That's it. That's it. That's what we do.
Maybe, maybe just questions and maybe in the new if you want to come set up already. Any questions?
No, so guys, hit me with your question.
So, what are the main sources of noise? I mean, would you
Well, it's the electronics, basically.
electronics? Okay.
You know, shop noise and what have you, which is
Right.
pretty much, you know, you can't get around it really, can you? So we would have to do some creative thinking. That's why really, I think the decision we came to was to use it for this particular purpose would probably be out of question. And that's why I personally would like to look at it in this context. Because there is a paper that was written years ago about this, which is where we got some ideas from, and in California. Because obviously, you know, the San Andreas fault is a really a major concern to them all the time. But also, I mean, you saw that devastating stuff in Turkey and Syria and whatever, you know, just a few years ago. You know, thousands of people dying. If you could help them with some kind of early warning, then I think that would be. And also, I think the size of signals we get from that, especially if you sit right on top of it, as it were, you know, on the fault line. We know where fault lines are, don't we? So if you could sit right on top of it, then I think the signals would be much larger. And therefore we'd be able to get above all the noise and therefore be able to detect it.
Would it be earlier than other seismometers?
So again,
Would it be earlier than other seismometers, like state-of-art seismometers?
well, the thing is, sorry, say that again.
No, so the other seismometers which pick up earthquakes. So
Well,
why-
they have, but the thing is, they're still. It appears that they're still not good enough. So I don't see this as an end in itself. I just see this if it could work, it could help. It could be another part to another thing to look at. And it could be really, really good. And you think, well, that's okay. You know, but obviously, you know, as research goes, you have to go in and see it. But I think it would be interesting. The other thing is that trying to detect stuff of very long wavelengths like this, I think it's intrinsically interesting, just as a science problem. Because pushing Maxwell's equations in limits, you know, right off to the scale limit, I think actually would be interesting in itself. Because just like we're talking about going from quantum mechanics, you know, classical world to quantum world, aren't we? Testing the equations to their limits. I think electromagnetic waves we could do that here, I think,
Well, I
in principle.
no.
And I think that would be, you know, if you found that Maxwell's equations didn't quite function at this sort of extreme level, that would be interesting, wouldn't it? Just in its own right, you know. So without saving people's lives. But if I can save a few people's lives on the way,
Yeah, it's maybe
I'm all for it.
This is the it's a website to see.
Right. Okay. Go on, good luck, Flack. Yeah,